So I'm kind of sad because this could be the last lecture video of the top 3 carbonyls. And not only that, but this could be the last lecture video for carbonyls in general. So it might make me sad and depressed and feel kind of lonely. But with those words that you've just heard, you are probably shouting for joy and screaming and yelling and probably ready to party over the weekend because you know that you no longer have to listen to the stories of the C double bond O anymore after this is completed. So whatever you're feeling, it's okay. I kind of understand. But this video is going to target the Claisen condensation. So another one of these special named reactions where we are taking some carbonyl groups and we are reacting and doing some funny things with them. But because we're talking about type 3 reactions, this is going to focus on probably the alpha or beta carbons. It's not going to really focus on the carbonyl itself. So first, the Claisen condensation is going to require 2 esters. So I'm just going to go ahead and draw down 2 esters that we want to use. So CH3, CH2, C double bond O, O, and CH3. Let's say that this is our ester that we want. And let's just make this thing a little bit simpler and just make it symmetrical. So CH2 and CH3. People tend to like when things are nice and pretty and even on both sides. Okay, so here is the ester. If I wanted to name this ester, let's do that little bit of review. If I wanted to name the ester, I name the piece attached to the O first. So this is ethyl, right? So ethyl's here. And then I name the longest carbon chain. So 1 carbon, 2 carbon, 3 carbons. So this is propane. I drop the E and add O8. So ethyl propanoate. And it requires 2 esters. And traditionally, what we most of the time see with Claisen condensation is the same ester reacting together. So I'm just going to write a pot plus, and I'm just going to rewrite the same ester that we started with. So we're going to assume that only one type of ester is in this flask, and that is it. And these 2 esters can actually react together if we give them something to stimulate this production. So what are the catalysts or reagents, other reagents, that are necessary for this reaction to go forward? Okay, well, I probably need to bring in some type of base, right? So we'll just bring in an ethoxy group. And this ethoxy group can scour for alpha hydrogens and pull an alpha hydrogen off. Okay, so that's the purpose of the base that we have brought into the solution. Notice that I've made it match. This is not a requirement, but because these ethyl groups are on the ester portions, well, I'm kind of making it match as far as the base goes. That is not a requirement, but that kind of cleans up the reaction process a little bit if we can keep everything the same. So that's why I've chose OCH2CH3, but really any base will work. You just got to be careful sometimes on what you choose, but for the most part it's okay. And then in step number 2, we're going to throw in some acid. And you probably know the purpose of the acid. It's to protonate something. It's probably to give a hydrogen off on something that will form as far as a new bond will go. So these are the 2 reagents that I need in order for this reaction to go forward. Okay, so what goes on here? Okay, so first, we're not going to talk really about mechanism that much. The mechanism we can easily draw out if we wanted. The base is going to target the partial positive carbon. The carbon's going to break the double bond to the oxygen. Oxygen's going to try to reform that double bond back on carbon, and then that carbon's going to kick off a leaving group, and in this case that leaving group is going to be the ester group, because esters are type 1 carbonyls. They have a leaving group involved. Okay, so with that said, if we want to skip the mechanism and not worry about it, we just understand base, positive, break, reform, leave. We end up with a CH3, CH2, carbon, double bond O with now a free site of attachment. Okay, well, the free site of attachment, we've got to basically provide that with something. We can't just leave it free. And the other ester molecule that we've drawn here, there is a possibility, that's one route of the synthesis, right? But there is a possibility of a alpha attack. Right? That's the whole purpose of this lecture, is to talk about what happens at these alpha carbons. And that's an alpha carbon there. And that alpha carbon has a hydrogen that it can give up. And that hydrogen can be removed if we put a base in solution. And you know what? We've got one. So some of the base can force one of the esters to kick off the OCH2CH3 group, and another one of the bases can look at the other ester and pull off the alpha hydrogen. And if it pulls off this alpha hydrogen, that's going to be the site of attachment now. So this CH2, this hydrogen gets pulled off, you have a CH that's left. Well, that carbon has a methyl group on one side, and this carbon has a C double bond O with a OCH2 and a CH3 that's there, and there is the new bond that is formed between my two ester pieces. So if I look, this ethyl portion of the ester is deleted, and one of these hydrogens are deleted, and this kind of generates CH3CH2OH for me as a byproduct. But these reagents allow me to splice these two esters together, and that is the reason that that happens. So this is what we term the Claisen condensation. Okay, now when I say that, you're probably thinking in your head, oh no, we've got Hell-Volhard-Zelinsky reactions, and now we've got Machel reactions, and now we've got Claisen reactions, and now I've got all of these type 2 reactions, and now I've got all of these type 1 reactions, and now I have all of these other kind of alpha carbon and alpha hydrogen reactions that are taking place. How do I keep all of this straight? Well, again, it's not the process of memorization. We do not want you to memorize reactions and memorize products. There's no way that you can do that in organic. Nobody can. But we need you to memorize and learn, is the better word, the mechanism that allow these reactions to go forward. Just like here. You know, I should immediately look at this and say, oh, well, I have a base here, and this base is going to attack something positive. Well, I have two options. One of those options is at the carbonyl, like we've talked about over and over and over in the top 1 reactions, because this is an ester. And the other possibility is for this base to attack the alpha hydrogen, because that's just what we've discussed. There is a hydrogen there that can be ripped off. So in one route, it's going to attack it, and a leaving group is going to form. In the other route, it's going to attack it, pull off a hydrogen, and these two pieces really come together, glued together, to form this spliced ester group for me that we see on the screen. So it's all about the mechanism here. That's what we're after. You need to be learning mechanisms. You don't need to be memorizing things that go on. So this is it, folks. This is the last video of the type 3 carbonyls. It's the last video of the carbonyl lecture portion. You know, if you look at the entirety of the carbonyls, you're looking at about 40 videos for the first round. You're looking at about 40 to 45 videos in the second round. You're looking at another 10 to 15 videos here. So in total, you're looking at close to 100 videos that target just carbonyl reactions. It is almost mind-blowing the number of reactions that we can do with these carbonyls. And the reason is because the family is so large, right? We've got carboxylic acids, and we have amides, and we have esters, and we have ketones, and we have aldehydes, and we have acid anhydrides, and we have these acyl halides that are all part of this family of reactions that can take place. So that's the reason that there's so many of them. But if you're clever, you're going to figure out that the mechanisms and the reactions are all very similar. Even though there's so many different functional groups, the reactions as a whole are very similar no matter what functional group that you're targeting. There's only a few instances where we have to be careful, and especially when we're looking at amides and when we're looking at carboxylic acids. You know, those functional groups, well, they're acting as acids and bases, so we just have to be careful how we handle those. But all the others, they're happening the same way, no matter what kind of nucleophile or reagent that you bring into the picture. So this is where we stop. I wish you good luck on the exam for the carbonyls. You are probably going to think it's going to be horrific. You're probably thinking that there's no way that somebody can pass this with an A or a B or maybe even a C average, but I guarantee you it won't be as hard as what you think it will be. There is a lot of material. The good news, though, is that the more material, the I guess you could say easier the test will be, because we cannot focus on details. We just have to focus on general overall view of carbonyls, not really the details and the exceptions that can happen with these reactions. So hopefully that makes sense. Hopefully you feel a little bit better after you hear that. So as long as you understand the overall grand scheme of things, I think that you'll be okay. Don't get yourself bogged down into all of the minute details that are happening with the mechanisms or that are happening with the reactions or the exceptions that we've talked about along this series of videos. So good luck studying, good luck on the last homework set, good luck on the exam, and wish you wonderful break. So if you're viewing this at the end of the fall semester, wish you a good holiday season, a Merry Christmas or Hanukkah or whatever you celebrate. And if you're watching this at the end of the spring semester, then I hope that you enjoy a very good summer, and I hope that you spend many days at the beach and not think about carbonyl chemistry at all. So I wish you the best of luck.